Hi everyone, welcome back. Today we're going to talk about, we're going to finish up with the light and matter interaction, okay? And previously we have gone over the full classical model, which, we treat the light, as classical wave, the electromagnetic wave, and then, use Maxwell equation and nonlinear equation, okay, to derive the nonlinear optics equation. And then the past few lectures, we start to quantization, quantize the light, right, using annihilation and creation operator. But then we're still treating the light, we're still treating the matter itself, right, as a classical matter, because we still keep using the nonlinear coefficient, for example, chi2, which is something that is exactly the same as the classical model, right? So, we can call the model, okay, a semi quantum model or semi-classic model. So here today we're going to talk about the full quantum model, where you treat the light, okay, with quantum mechanics, and also you treat the matter with quantum mechanics. And of course we're just going to go over the simplest one, okay? We're not going into any detail here. Okay, so the way that we start with the quantum model, full quantum model. Okay, the simplest way, if you think about it, simplest light and matter interaction in a quantum model would be if you have one photon, okay, and then you interact with one atom, right? At least in theory, that's the simplest. Of course, in experiment, that's not the simplest one. Okay, so if we want that to happen, then what we can do is that we can assume, okay, we have an atom, and then the simplest atom, we can assume, okay, it has two energy level, a ground state and an excited state. Of course, all atoms has high energy state, but for simplicity, okay, we ignore them. Okay, we just assume there are only two of them, right? And for the light, okay, you can assume traveling wave, right? The light, going from left to right or going from one direction to another. But in reality, okay, because light and matter interaction, a single atom, single photon interaction is very weak. So usually, what you need is you need a cavity, okay, a pair of mirror, okay, to trap the light that go back and forth to interact with the atom. Okay, so you increase the strength of the interaction. Okay, and we already know how to quantize light inside a cavity, right? So this part is fine. Okay, so so the goal for today, okay, is to understand this simple system. Okay, what will happen? Let's say if you have a photon and then your atom is on ground state, and then what will really happen, right? Or if there's no photon, then you have an atom in excited state, then how the system will evolve with time and what are the eigenstate of the system. And you can just picture this, right? How this will happen if there's a photon coming in, okay, inside this cavity, and it's with, the frequency is close to the energy difference, okay, between ground state and excited state. Then you can imagine what will happen is that when the light come in, there is a probability, okay, of it being absorbed by the atom, right? And when this happens, the atom will go to the upper state. And when it goes to upper state, then there's no, because you already absorb this photon, then there's no photon in this cavity. And then the atom, okay, will go through, it's possible to go through emission, right, emit that photon. So you can imagine, okay, there will be a absorption, emission cycle, okay, happening inside this system. Now, how can we formulate it? Okay, how can we formulate the light and matter interaction? And because we're using the full quantum model, by the way, this is called JC model, this model here. Okay, JC model. So because, okay, the way the way that you when you try to solve a quantum system, the number one thing you need to do is to write down the Hamiltonian. Okay, so so here, how do we write down the Hamiltonian? Well, we can. Well, the Hamiltonian is composed of two components, right? First is the Hamiltonian of the atom. Okay, and then you have the Hamiltonian of the photon. Okay, the Hamiltonian of the photon is relatively simple because we know it's h bar omega a dagger a plus 1/2, right? So we'll leave it to the end. We first look at what the Hamiltonian of the atom would be. Okay, and this part, Hamiltonian of the atom. Okay, what is Hamiltonian? Right, Hamiltonian is just the energy of the system, right? So now imagine, okay, what is the energy if your atom is in ground state? Okay, that would be E1, right? You can assume, okay, this is E1 and this is E2. And how do you express your atom is in E1? You use this, right? Okay, the right bracket and left bracket. Okay, this is actually the matrix expression of a Hamiltonian, and then the same for the upper level E2. Okay, so this is the matrix expression. Okay, so 1 and 2 are the eigenstate of the atom. Right, if you write it in the matrix form, then it would be E1, 0, 0, E2. Right, and then it's very easy. You can see that h bar, okay, for psi 1 equal to E1, 0, 0, E2 times 1, 0 equal to E1, 1, 0. Right, so this is equal to. Okay, so you can see that, okay, by writing down the Hamiltonian in this matrix form, you automatically get Hamiltonian act on your ground state, give you ground energy and the ground state. Okay, you can also prove that it's also true for E2. Okay, and so this is the Hamiltonian of the atom. Okay, and then the Hamiltonian of the photon, we know that. Okay. Right. Okay. This is exactly the same as what we have. Well, what we derived in the past few lectures. Now, when we write it down like this, it's assuming there's no interaction, right? It's not. It hasn't include the interaction between atom and photon, because atom is just. It's non-perturbed or non-interacting Hamiltonian. Photon is just the non-interacting Hamiltonian. Now let's think about it. Okay, now let's think about it. What would happen? Okay, how to include the interaction into the Hamiltonian? Okay, so the common way to do it is just to write down, okay, the potential energy induced by this interaction, right? Induced by this interaction. For example, if you want to, let's say there's electron 1, electron 2, right? If you want to charge 1, charge 2, right? If you want to include the interaction between these two charges in your Hamiltonian, then what you need to do is simply write down k, q1, q2, r squared, right? Where r is the, r. Okay, where r is the distance between them. Okay, this is the potential energy between these two charge, okay, and this is how you usually include interaction. Okay, you just by writing down the energy. Okay, and so here the question is, okay, if we allow light and matter, okay, be at the same, like if we allow them to overlap, for example, this is atom, and there's a light, right? Atom is much smaller than the wavelength of a light. And let's see, this is the representing the electrical field of the light. Okay, then the question, okay, we want to ask is that, okay, what energy changed, and then, well, what potential energy change, and then what is it, right? And the simplest way to understand this is that when we say, okay, when we write down an atom, right, we say, okay, there's energy level. What we're really talking about is just the electron, right? Electron on the outer layer, right? This is responsible for all this electromagnetic interaction, right? The nuclear is kind of shielded inside, right? So when you have an atom here, okay, it has an electron here, and then it's in the electrical field of the light, right? Then you can imagine, okay, then there must be a potential energy, right? Because if you put a charge in an electrical field, there's potential, right? So what is that potential? Okay. For example, if the electrical field is like this side, E, okay, and then you put your charge here, Q, right, Q, and let's say this is 0, okay. Let's say this is potential energy 0. Then the then the potential energy here at Q is simply the energy you will need to move the electron from this spot, from 0 potential energy, to this location. Well, let's say it's X, right? Let's say it's X. Right, so and I think from EM field, you guys all learned that, okay, the potential energy is E. Okay, this is positive X, right? So this X is actually a negative one. So it's Q minus EX, right? It's the energy. Okay, it's the energy you would need to move the electron from here to here, right? And X here, okay, because we are moving against the electrical field, right? So X is a negative, X is negative, and there's a minus sign here. So you will see you need you need a positive energy to move it from here to here, which increase the potential energy, okay, of the charge, okay. So we can use the same. We can use the same idea to include the potential energy of the electron in the atom. Okay. The potential energy is the electron of the atom, okay, in the electrical field of the light, right? The electrical field is provided by the light, and then the charge, okay, is from the atom. Right? So what we can do is that we can write down minus Q, okay, Q, I think here we should do this, E X, okay, E and X, and E and X, okay. So this is just the potential energy of the charge. This is the potential energy of the charge of the atom, okay, in the electrical field. My apology for the, it's not very smooth, the lecture, because it's been quite a while. Well, it's been a year since last time I recorded a video, in an empty room, and then it's actually not that, well, still I haven't, I just don't enjoy it, to be honest, okay. So, okay, so what is the electrical field? Right, electrical field of the light, okay, from what we learned in previous class, lectures. Okay, it's this. Okay, this is the electrical field of the light. Okay, electrical field of the light. And so here you will see that, okay, there's a position dependence. What it means is that because the electrical field is, the electrical field inside the a cavity, okay, is a standing wave, right? So when you put the electron, well, when you put the atom in different positions, you will see different amplitude of the electrical field, right? So if you put it at the node, okay, at the zero position, for example, z equals 0 or kz equal, pi, n pi, then you will not see any electrical field and you don't have any interaction. Okay, so usually when people actually do the experiment, what they would do is that they would try to put the atom, okay, in the maximum electrical field position, which in here, okay, is this equal to 1. Okay, this equal to 1. So we just assume, okay, sine kz is 1. Okay, sine kz is 1. Okay, and what we can do is we can now plug in this into here. Okay. 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 Now I want to explain a little bit what this x is. Okay, this x is the position, okay, of your charge, right? You can think of it as the 0 point doesn't matter, right? Because what really causes energy is the 0 point is just adding an offset, okay, in your potential well, right? So eventually what will really happen if you kind of try to visualize this is that the electrical field of the light, okay, because it can have a Coulomb's force on the electron. So what the electron will do is that it will move, okay, slightly from its original position, okay, and thus create the interaction. Okay. Okay. So this is Hamiltonian of the atom, Hamiltonian of the photon. Okay, and now we need to learn how to simplify them. Okay. So some of this content were actually, like in the first year when I taught this, I think this was taught in the first month of this lecture. But then at the time, at least I got the feedback was that it's a little bit deep, so that I removed them since the second year. And so kind of here when it's probably the first time you guys see this in this lecture, so that it's a little bit of like probably unfamiliar, okay, but we'll just keep going. So here what we are going to do, if you look at this Hamiltonian, okay, it's not clear, okay, it's not clear. I would just say it's not clear what you can do with it. But then here we try to use another approximation that really help to simplify things. The approximation we want to make, okay, is that this interaction is this electrical field is relatively weak. Okay, it's relatively weak. It's not going to change the eigenenergy of the atom. Okay, it's not going to change the eigenenergy of the atom. So what that means is that we can treat this as a small perturbation. Okay, so it means the atom. Okay, if you write down the atom, wave function, what it means is that instead, so each, what it means is that the ground state and excited state the mathematical form of the ground state and excited state stay exactly the same. Okay, they're not change. They do not change because of this small perturbation. What's really changing, okay, is the superposition coefficient in the front. Right, because of this interaction, it will change the distribution, okay, between the ratio of the probability in the ground state and the probability in the excited state. So it's really what it's doing is that it's induced the electron to go, to move from eigenstate to another eigenstate. Okay, it's not changing the form of the eigenstate itself. Okay, so this is the first perturbation approximation. The second one is that, okay, we assume that the electron can only go from can only stay in the ground state and the first excited state. Okay, although in reality, okay, you can even go to a higher state, but then we, for simplicity, we ignore them. And this approximation, okay, works pretty well, okay, as long as the light, okay, the frequency of the light is approximately close to the energy difference, okay, between the ground state and excited state. Okay, so what's the benefit of making this assumption? Okay, the benefit of making this assumption is that now we know that the interaction, okay, will not change our eigenstate, only changing the parameters, okay, of the in front of this state in the superposition. So what we can do is that we can express this interaction term in matrix form, right? In the matrix form, in the basis of 1 and 2, right? Ground state and excited state. So the way that we do this, okay, is actually quite, this is, yeah. Okay, it's quite standard in quantum mechanics, is that whenever you try to convert, for example, an operator, right, from its continuous form into the matrix form, then what you do is you multiply to the left and to the right the identity matrix. And the identity matrix is just the sum of all the eigenstate, left bracket and right bracket. Right bracket and left bracket, okay? And if you don't know what this is, you can search identity operator in quantum mechanics on Google, okay? And then I think a lot of the textbook, a lot of the forum, okay, actually talk about this. So what we can do here, okay, is that we apply, okay, we call this H interaction. Okay, the interaction is equal to the same interaction Hamiltonian, and then on the left and on the right we multiply with the identity matrix. And what the identity matrix here is, right, because we only have two states, is simply 1, 1 plus 2, 2, right? And then Q EX let's write it down as Q X E. Okay, this part is just E, right? And then on the right, it's the same. Okay. Okay. Now, how to calculate this? So first of all, one thing we can see immediately is that the electrical field, it's not part of the atom, right? It's electrical field. It's just an electrical field you add to the atom. So when you have your atoms, state, right, trying to do inner product with the electrical field, you can simply treat the electrical field as a number or a vector, simply as a vector. So this part, you move it to the outside. Okay. And X, right? X, because it's really the position of the electron, right, in the atom, right? So X actually is related to X when you do the inner product. Okay, this is the atom's X, right? So electron's X, right? So this one actually give you a non-zero. This one will actually give you a number here, right? So what you will see here is that you will see. Okay, you expand all this term 1 QX, okay, 1 1, right? And then you also have two QX 2 2, right? And then we have the cross term 1 QX 2 2, and plus 2 QX 1 1. Okay, and and when we write everything down in a matrix form, right, we already assume that we know the mathematical expression of the eigenstate. And this is actually not difficult, right? Because like when you do experiment, when you actually put an atom inside the cavity, you have to know, okay, what atom you put in there, right? So for different atoms, it will have different eigenfunctions. Okay, so when you do this calculation, you will see that by definition, right? Let's see. By definition, let me write it down this way. By definition, psi 1. Okay. Psi n, an operator, psi m. Right. By definition, this is just the expected value. Well, not really. Okay, it's similar to the expected value, but this is the inner product. Right. When n equals to m, we know then this is the expected value for A when your quantum system is in psi n state. Right. So here we can very easily tell. Okay, then 1 1 is the expected value of x when psi is equal to ground state. Okay, and the same for 2 2. Okay, same for 2, 2. And and one way you can do this, okay, is that, okay, you can look at what atom you have and redo this calculation. But there's a very simple trick. You can see here that for all the atoms, for I'll say non-polarized atoms, you can see that this term will always be 0, right? Because if this is your atom's core and then there's the electron going around, you actually have a spherical symmetry, right? So when you try to average where the electron is, okay, around the atom, you always get 0. Okay, the electron on average, okay, is always here, right? Because you have the same probability on the left and on the right, and when you average that, that's 0. Okay. So this goes to 0. This goes to 0. Okay, it's 0 for all. It's 0 for all. It's 0 for all eigenstates. Okay, and then, well, my apologies. Sometimes it's difficult to focus when I'm the only one in the room. Okay, and one thing I want to correct is that I think I said polarized atom. So for atom, I think none of them are polarized. Only molecules can be polarized. Right? So if you put molecules here, then if they're polarized, then you can get a 0 here. Okay, so that's great. That means here that for atoms, we see here we can just cross these terms. Okay, we can just cross these terms. We can just we just know that, okay, they're not they're 0. Okay, and so we're left with these terms here. Okay, these terms here. And previously, you already know, right, from what I just wrote down here, left bracket 1 operator right bracket, what that gives you is integration, right? This is integration right, this is just the integration of this. Okay, so now if you look at this integration, you can clearly see that, okay, it's a function of x and then you integrate over x, right? Okay, x is a vector, 3-dimensional. So after this integration, this term should just show up as a number, right? Should show up as a number. So we can actually define this as mu, because 1 and 2, so you can say mu 1, 2. Okay, it's a vector, mu 1, 2. Right, because here you are a vector, so that when you have x, y, z, okay, 3 components. Okay, so this mu 1, 2, okay, you see that this is purely defined. This is purely determined by the property of the atom itself. Right, it has nothing to do with your light. Right, psi 1, psi 2 are the wave function of your atom, and Q is the charge, okay, effective charge of the outer electron in the atom, and X is just a variable, right? So this integration is fully determined by the structure of your atom, right? So so here, okay, to not lose generosity and also to kind of simplify the calculation, we assume that, okay, whenever you find an atom, okay, put it here, you will be able to calculate this. Okay, so you can treat mu 1, 2 as just as a vector, as a known vector. Okay, and the same apply to the second term here, 2, and then psi 2 okay. You can see that this integration, by that definition, okay, would be mu 2 1. Okay, mu 2 1. And also, if you really look at it, you'll see that this integration is simply the conjugate, right, of this one. Right? You can see that if you take conjugate, then mu 1, okay, mu 1, and then star, okay, will come to here. And then also because x, the operator x is just itself x, right? So you can actually switch the order, okay? So, yep. So here later we'll see that this is simply just mu 1, mu 2. Okay, later we'll actually use this equation, this relationship. Okay, so so now we can simplify. Okay, we can really simplify. Let me take a look here. I think I miss minus sign. Okay, minus sign. There's minus sign in everything, in front of everything. Okay. Okay, minus sign from here. So we have minus mu 1 2. Okay, 1 2 plus minus. Okay, minus mu 2 1. Okay, 2 1. Okay, and then this multiply with okay, I think one more definition problem. Okay, Q is, I think Q is moved in the front. Okay, so mu 1 2, I think from the definition I have here, doesn't include Q. Okay, doesn't include Q. So Q will be here. Okay. Okay. So if we put this matrix form of the Hamiltonian here, okay, back into the atom's Hamiltonian, what we will see, the Hamiltonian of the atom okay, it's just E1 plus E2. Okay, and then here, right, minus and then we know E is this form, right? So let's erase all this and then plug in the electrical field of the light and see what will happen. Okay. One second. I think there's a mistake in my note. If we look at the first page of the JC model, I think in the middle, in my definition, Q is not included in mu, but later I remove Q again, kind of insert it into mu. Okay, so let's just, it actually really doesn't matter. It's a definition thing. It's whether mu12 include Q or not. Okay, let's just make it simple. Okay, Q is absorbed into mu21 and mu12. Okay, yeah, sorry about that. Okay, now we plug in E. Okay, E into here. Then let's take a look at this term first, right? Okay, the beginning two terms are the same. Okay, minus mu12. Okay, and times. Okay, direction. Okay, epsilon naught. Okay, 1, 2, A plus A dagger. Right, this is this term. Okay, and then we can do the same to the second term, which is mu21 2. We don't need bracket here. Okay. Okay. So now let's kind of look at the meaning of these terms. Okay, the meaning of these terms, and then we can look at them one by one. So the first term, okay, you can get from here is 1, 2, A. Okay, 1, 2, A. What does that mean? What does that mean? If you think about it, if you apply this Hamiltonian on, let's say, on an atom, okay, on the system, right? Atom with light in it, right? Electron state. And what this would do? What this would do? Actually, let's look at this first. Okay, the A dagger one. Okay, so look at this term. Okay, later we'll come back to the A term. So what this would do on a state that include atom and also include photon, right? It's kind of the state that you use to wave function you use to describe the entire system. Then, if you look at it, what it really does, okay, what it really does is that to the atom, right? If your atom is in state 2, right? If you're in the excited state, then what this would do, right, is that it will give you state 1, right? So this operator here, 1, 2, is actually a lower operator. It's kind of the annihilation operator. What it does is that it moves the electron, okay, from the upper state to lower state, to ground state. Okay, this is what this part do. Okay, and reversely, you can kind of see that 2, 1. Okay, what this would do is that it will move the electron from ground state to excited state, right? Because if you act this on the ground state, then 1 and 1, okay, they're 1, and then you move to 2, right? So this is lower operator. This is this is kind of excite the atom, okay, operator. And what about this? This A dagger, okay, if you act on any photon state, then what it would do is that it will add 1 photon, right? This is the creation operator. It will add 1 photon to your system. Okay, so in total, what this operator really does, okay, is that it moves the electron in the atom from state 2 to state 1. okay, from state 2 to state 1, and at the same time emit a photon, right? So this operator is actually corresponding to emission, okay, of light from the atom, okay. And similarly, okay, we can see, okay, from here 2, 1, right? If you are 2, 1, okay, if a 2, 1, and then A, okay, what it would do is that your atom, okay, would, if it start from the ground state, then what it would do is that, okay, it would be raised to excited state, okay. And how does this happen? Okay, it's happened because you absorb a light, right? You reduce the number of photons by 1. So this process, this operator combination, this corresponds to absorption and this corresponds to emission, okay. And of course you might wonder, okay, what if this operator act on ground state, right? Act on ground state. Then what really happens is if that happens, right? So 1, 2, A dagger, act on ground state, which is 1, and then you have some photon state here. And this is always 0, okay? It's because, yeah, it's because 2 and 1, okay. 1, 2 here are the 1 and 2 here, right? They're not photon number. So 2 and 1, okay. Let's rewrite them a little bit better. 1 come to here, and then A dagger act on the photon state. It looks like, okay, you might increase the photon number by 1, right? But really happen is that the 2 and 1, because the inner product of them, the excited state and the ground state, because they're orthonormal, so this term is always 0, right? So when this term act on the ground state, okay, act on the ground state of the atom, okay, it does nothing. It's 0, okay. It's 0, okay. So it wouldn't change the system at all. It wouldn't add any energy or cancel any energy, okay. So okay, so this is how we get to, you know, this 2 state here. One of them is mu12 EX epsilon naught, and then 1, 2, A dagger plus, right, mu21 EX epsilon 2, 1, okay, A, right. These are the 2 terms that we just discussed. And okay, then we still have 2 other terms left, right? The two other terms is 1, 2, and A. Okay, 1, 2, and A. And we can use the same. Physics picture and then see, okay, what this term is really about, right? So from here you can see the 2 first and then get 1, right? So it corresponds to atom or electron, okay, going from ground state, excited state back to the ground state. And what A does is that A is reducing the photon number by 1, right? So it's actually an absorption process. Okay, so if you look at this operator, what it does is that it absorbs a photon, and then your atom move from excited state to ground state. Okay, and I think that kind of, well, you guys can all immediately see, okay, this is not right, right? Because you lose energy for the photon, and then you also lose energy in the atom, right? So this term, okay, this term actually violates energy conservation, and so this term just get canceled. And there's a more rigorous way, okay, to prove this is if you carry, frequency of all these terms, you will see, okay, this term has a very fast, I think. This term will have a fast oscillation, okay. Okay, and then you can do a small integration on this and then show that, okay, this term on average is 0. Okay, it will not contribute to any observable effect. And so there are two ways kind of you can throw it away, right? One is through a more precise calculation, the other is just simply using energy conservation argument. And the same can apply to this operator, okay, 2, 1, and then A dagger. Right, 2, 1, and A dagger is you move from ground state to excited state, and then at the same time you create a photon, right? So you add energy in your photon, and then you add energy in your atom. So again, this is energy not conserved, so you have to throw away this term. Okay, so okay, after all this, then we can. I keep missing minus sign. Okay, after all this, then we can kind of now write down the Hamiltonian. Okay, the reduced Hamiltonian. Right. Hamiltonian is mu12 EX okay minus okay. So at this step, well, when we arrive at here, we actually is already halfway, okay, of solving this entire problem now, because we write down the accurate Hamiltonian, and then the Hamiltonian is fully quantized now, right? So the Hamiltonian is expressed by, the matrix form of your atom, right? 1, 2, 1, 2, 1, 1, 2, 2, okay, 1, 2, 2, 1. So it's quantized, right? You can only be at state 1 or state 2, right? It's not a continuous state anymore. And then the photon, okay, is also fully quantized, expressing by A dagger A, and then the electrical field here, again, we use quantization here so that your A dagger and A, they're operator here. So arriving here, we, get the fully quantized Hamiltonian of this very simple system where you have, photon in the cavity, and then you have one atom, right, in the cavity. And the second half of this class, we're going to solve this equation, and we just, we're going to show you, show you guys one or two interesting thing about them. Okay, now let's come back and solve this JC model, solve this quantum system. Okay, the first thing we can do now, we have the atoms Hamiltonian and the photons Hamiltonian. We can combine them, right, to get the Hamiltonian of the whole system, right? And what we will get is that we can first write down the Hamiltonian of the photon, okay, in the front, okay, and then of course then followed by the Hamiltonian of the atom, okay, and now here, okay, if you look at here, epsilon naught is the electrical field of the electrical field intensity of the vacuum, right? So it's a fixed number when you quantize the cavity. And then mu21, mu12, they're just mu12, mu21, they're just the property of the atom, right? And then we also know mu12 equals mu to 1. Okay, conjugate. And here just for simplicity, okay, this is for simplicity, and it's not necessary. Okay, then it will not change any result, but here just for simplicity, okay, we assume these are real number. Okay, we assume they're real number, then we know mu1, 2 is equal to mu2, 1. Okay, this is assumption that you don't have to make. Okay, then what we can do, okay, is that we don't have to carry this number around now, right? Because mu1, 2 times x give you a number, and then times epsilon naught, which is also a number here. So what we can do is we can define, okay, just to simplify the notation, we can define h bar g, okay, is equal to minus mu1, 2 e1x epsilon 0. Okay. And so we can get plus h bar g, okay, plus h bar g, 1, 2, a dagger plus 2, 1, a. Right. And here, okay, here, why do we have a minus sign here? Okay, the reason is for mu, right, mu1, 2, okay, we know that inside there's a Q, right, the charge of the atom, the charge of the outer electron, okay, is actually composed here, and then it's included here, and then we know normally Q, okay, is negative, right? The electron has a negative charge. So when this multiply with this, okay, it gives you back to a positive number. Okay. But here, from here on, okay, we just treat G as a number. Whether it's positive or negative, it actually doesn't matter that much. Okay. So this is Hamiltonian. Okay, and we want to make two more adjustment, right, to make this Hamiltonian actually look even better. So the first is that if we look at the 1/2 here, right, in the Hamiltonian, it actually doesn't. We know that the 1/2 comes from quantum fluctuation, but then in terms of energy, it really doesn't need to be here, right? Because you can readjust. For example, you can readjust the zero energy, potential energy, right? That's something you can assume. Okay, then you can eliminate this. Right, you can eliminate this. And the second thing is about the energy E1 and E2, right? When we write it down like this, E1 and E2, okay, the equation doesn't really seem very symmetric. Okay, so if you look at other term, right? If you look at here, okay, 1 and 2, they're quite symmetric. So we want to make this two term look symmetric. And the easiest way is to readjust, okay, it's just to assume, okay, in the middle, okay, of their energy level is your potential energy 0, right? So you readjust. And then E1, okay, the energy of E1 now become, it's a minus number right now, right? So become minus E2 minus E1 divided by 2. Right, if you set here at 0, right, then you are half of the energy difference down, okay? And then for E2, you are half of the energy up, right? So E2 minus E1, 2, right? So now if you look at their energy, okay, now you're symmetric. You're only off by a minus sign, okay? And then we can further define, right? We don't want to carry E2 and E1 around. It's only their energy difference, okay, that really matters here. So we can define h bar capital omega equal to E2 minus E1, okay? So by moving the zero energy into here, we can actually change these terms into minus h bar omega divided by 2. Okay, and then this is plus. Okay, so if you look at it, the energy difference between ground state and excited state is exactly the same as before. The only difference is the absolute energy, right? And we know that for light and matter, well, for the atom, the absolute energy really doesn't matter. What it matters, for example, whether it absorbs the photon or not, only depends on the energy difference between ground state and excited state. Okay, it really doesn't matter what your ground state energy really is, right? So that's the reason, okay, we can redefine the potential energy, okay, to make this look more symmetric. Okay. Okay, now something further we want to do, okay, is that we want to, because each of this, okay, they have specific meaning, right? They correspond to specific physics process, right? For example, this one correspond to the atom go from excited state to ground state. This one go from ground state to excited state. So we can actually assign them, okay, with specific, specific operators instead of just writing 1, 2, and 2, 1. Okay, it's further just to simplify the notation, and actually people do that all the time, so that a lot of time people just don't write it like this. Okay, they will write in the form that I will just show you right now. Okay, so now if we look at this term here, okay, one simplification we can do is that if we write this in the matrix form, right, then it's h bar omega divided by 2, okay, divided by 2, and then okay, minus sign in the front. Right, if you write down this in the matrix form, then what you get, okay, is h bar omega divided by 2. 1, 1 is the first component, and 0, 0. Okay, this is second component, 1. Okay. And I think I made a notation mistake in the note, right? In the note, I think I defined this, I wrote down sigma z, the Pauli Z matrix as, okay, this is not correct, right? The Pauli Z matrix is this. Okay, it's this, right? 1 minus 1. So what we end up with here, okay, is minus h bar omega divided by 2 and Pauli Z matrix. Okay, Pauli Z matrix. So pay attention to the error I have on the note. Okay, and then this and this, okay, what they are, okay, if you write down as a matrix form, 1, 2, okay, is right, it's this component, and then we know that yes, and we know that the function, okay, the outcome, okay, of applying this matrix on an on the atom state is it move the electron from excited state to ground state, right? So this is lowering operator. Okay, so we define, okay, this is definition. We define this as sigma minus sign, okay, it corresponds to this specific matrix. And then you can do the same for you can do the same for 2, 1. Okay, 2, 1 would be 0, 0, 0, 1. Sorry. Zero, and this is by definition. Okay. This is an operator, okay, that move your electron from ground state to excited state, okay, using the plus as denotation. So that eventually what you get, okay, is h bar omega, a dagger a, okay, minus h bar omega divided by 2, okay, sigma z, right? And then plus h bar g, okay, sigma minus a dagger plus sigma plus a. Okay, so this is the form that people like commonly use, right, for JC for atom and photon interaction, right? This is the energy of the photon, energy of the atom, and this is the interaction correspond to. This is correspond to emission. This is correspond to absorption. Okay. So one thing I want to just briefly mention is in some papers, or in a lot of papers, and in Wikipedia, you will see that the sign here is plus. Okay, and this is due to the definition of what is the matrix definition. Right. So I think in our definition we have say that the ground state is 1, 0. And then the excited state is 0, 1, right? And then okay, 0, 1. So if you flip, okay, if you flip the definition of the matrix, you actually flip the sign here, plus and minus. So actually, it's just the sign here, okay, follows the definition of your matrix. So in the future, if you see, okay, here is a plus sign in the paper or in some website, it doesn't really matter. It doesn't change the physics at all. Okay, now let's okay, let's solve it. Okay, let's solve it. So we're already at a form that cannot be further simplified. So the way that we solve it, okay, is to it's actually, we actually need to make assumptions. We need to make assumptions. We assume, first of all, we assume that when atom is at excited state, okay, there's n photon in the cavity. Okay, there's n photon in the cavity. You can so n can go from 0 to 1 to 2, okay, to infinity, right? 0 photon means that you start from here, and then you can if you choose 0 photon here, then you will see that when it transits to ground state, then you have 1 photon. Then this would be a truly 1 photon, 1 atom interaction. Okay, and then when your atom is in ground state, okay, then of course, due to energy conservation, you'll have n plus 1 photon, okay, n plus 1 photon in your in the cavity, right? So if we make this assumption, okay, if we make this assumption, we know that, okay, we can combine, okay, the atomic state and the photon state, the notation, right? Because we know that whenever we have 2 in the atom state, right, the excited state, then you always have n photon. And if you are in the ground state of your atom, then you always have n plus 1 photon, okay, in your photon state. So that we can kind of use the matrix definition now. Okay, previously we defined this as 0, 1. Okay, we define this as 1, 0. Right. So before we actually run any calculation, what we need to do now, okay, is that because we redefine how we write down, how we redefine the matrix here, right? So we actually have to rewrite the Hamiltonian, okay, in terms of the matrix form, right? So the way to do this is fairly simple, right? If you want to know, for example, you want to know this, let's call this 1, this is 2, okay, let's give you a prime here, okay? If you want to know the first element, right, you have C11, C12, well, let's use H. H11, H12, H21, H22, right? Then if you want to know H11, then what you do is you apply 1, H, and then 1, right? You calculate this term, and then it will give you the number here you get is will be your H11, okay? Then we can do this on here, right? On here, okay? So H11, 11, okay, would have n plus 1 photon, okay? N plus 1 photon. So when you when this was applied to this term, then you will have n plus 1 h bar omega, right? This is the first term, okay? And then the second term here, okay, second term here, you're at the ground state, right? You're at ground state, so your energy is h bar omega, right? Your energy is h bar omega. And then the interaction term, okay, the interaction term is 0, right? Because we know that you're at the, you know, simply by looking at this, this term, okay, would change from ground state, change from excited state to ground state, but you're already at ground state, so this term is 0. This one would change from ground state to excited state, okay, that's fine. But then when you multiply again on the left-hand side, when you do inner product with the ground state, okay, this term, okay, because they're orthogonal, you will actually get 0. Okay, so this is the first matrix element, it's this one, and then we can calculate the 2, 2. Okay, so 2, 2, well, it's the same thing. You have n photon, then you have n h bar omega, and then you're at excited state, so you're at h bar 2, right? Okay, so now the difficult part is the, well, it's not really difficult, but the part would be the cross section h12, right? Okay, so for the cross section, it's actually quite obvious. One thing is that, okay, on the left-hand side, 2 and 1 doesn't have the same photon number, right? One is n, the other is n plus 1, and these two states are orthogonal to each other. So that when you do inner product on the first term, okay, it becomes 0. It's the same, okay, for this, because sigma z doesn't change your ground state or excited state, right? So eventually when you do excited state and ground state inner product, it's again 0, right? So the only contributing factor here would be these two cross section here. So let's first write down h bar g here, okay? And then on the left, 1 prime is 1 n plus 1, okay? And now this is the interaction term here, okay? On the right-hand side, you have 2, right? So this is 2n, right? And so now we look at this 2 term here. Right. So what this term would do, okay, this term, okay, if you look at it, this is even rise from ground state to excited state. If you're already at excited state, this term will go to 0. okay? And what about this? Okay, this one, from excited state to ground state. Well, this one will get from excited state to ground state, which is nice, and this one will rise the photon number by 1, right, by 1. So this one you will get h bar g, okay, when you rise it to here, so you have okay, I would say 1 n plus 1 . Okay, and when we look at this term here, okay, this acton 2 is just 1. Now the question is, what is A dagger acton n? Right, A dagger acton n, we know in the past is that, okay, it's actually square root n plus 1. Okay, here's 1 n plus 1. Right, so overall, okay, this term, okay, is n plus 1 h bar g. Okay, this is the intensity. This is the element of h1, 2. And you can also calculate h21, okay, which is 2 h bar 1. And then you can kind of see that this is the same stuff, h bar g 2 n. And then you have sigma plus a 1 n plus 1, okay, which is also n plus 1 h bar g. Okay, so overall now the Hamiltonian is very clear now. Okay, so okay, for the diagonal term, you have the energy here, n plus 1 h bar omega minus h bar omega 2. Okay, and then here is n h bar omega plus h bar omega divided by 2. Okay, and you can already see there's a special situation when the photon energy omega, okay, or the energy of the cavity omega, small omega, is the same, is equal to the capital omega, then these two terms, okay, will be the same, right? So you can see that the critical difference here would be the energy difference between these two, right? Otherwise they are the same. Okay, and then here you have the cross term is and then we know that the off-diagonal term, okay, correspond to the interaction strength between the two eigenstates. So here what you can see, okay, is that when you increase the number of photons, right, you increase the number of photons you have in the cavity, you actually has a stronger interaction between the light and the atom, right? You can flip. It's easier, okay, to move the atom from ground state to excited state and excited state back to ground state, and that makes perfect sense, right? It's like when you have more photon, that means that you have your electrical field, okay, of the light is stronger, right? And then so when your light is stronger, then it's easier to drive, okay, your atom from ground state to excited state and excited state back to ground state, and okay. And one interesting thing I want to point out here, this is purely from the quantum effect. Purely from the quantum effect, is when n equals 0, right? When n equals 0, when your light is when your atom is at excited state, okay, there's no photon in it, you still have a non-zero off-diagonal term. Okay, non-zero off-diagonal term. What that means is that even if, okay, you just put an atom on the upper state in a cavity, right? The light, okay, you still have off-diagonal term, you still have the interaction between light and matter that can drive the electron from upper state to lower state. And why is that? Okay, the reason for that is because you have the vacuum fluctuation, right? At vacuum, you still have non-zero electrical field. And from the mathematics, when n+1 show up, it's really a dagger ecton n give you n+1, okay? And yeah, so this is the origin, okay, of this. And you can kind of imagine now, this is a very famous discovery, I think in the 1950s or 1960s, and then, you know, constantly being observed experiment is that just by putting the atom in a cavity, okay, just by the atom interacting with the vacuum, okay, there should be some oscillation that you can observe, okay. Now one final change, okay, we want to make to the Hamiltonian. All these are just trying to make the calculation next just simpler and easier, right? We want to something we want to show here is that we want to, if you look at here, we already said that if you want the light and the atom to interact coherently, then of course you want the frequency or the energy of them to, you know, closely match, right? And also when they match, if the small omega equal to a large omega, then these two terms will equal to each other. So it's very useful, okay, if we define, let's see, where is it? Okay, if we define delta omega, okay, is omega minus capital omega, right? We define the frequency difference among them, right? So that the first half of these two will be the same. Okay, the only difference will be this one. Okay, if we do that, then we can plug in this. We can see capital omega will equal to omega minus delta omega, right? So here it will be 1/2 minus h bar delta omega. Okay, this will be n plus 1/2, okay, h bar delta omega. Okay, so this way we kind of further make our Hamiltonian kind of more symmetric or simpler. Okay, now let's solve the, as we discussed before, right, we have two things we can solve. One is the eigenstate, eigenenergy, okay, of this new system. And the other thing is, okay, if we start from, for example, ground state or excited state, and then we let it go, and then see how the system evolves with time. And we can solve this one by one. Okay, first, we start with the simpler one, is the Hamiltonian, is the eigenstate of the system. Okay, we know that to solve the eigenenergy, what you can do is that use H act on eigenstate equal to the eigenenergy per psi. Right, you can solve per psi and E at the same time, or you can simply solve the the eigenvalue equation, which is the determinant of Hamiltonian minus your eigenenergy and the identity matrix. So this would be, okay, n plus 1 h bar omega minus h bar delta omega minus E. Okay, let's put minus E here. there's a 2 here. I'm sorry, I made a mistake here. This is plus. Okay. Yeah, because capital omega and delta omega is different sign. Okay. Well, it's yeah. Right now it's 10 p.m. at night, so kind of. Unfortunately, I don't have other time to record long video like this, so I have to do it at night, and my brain is not as fast as during the day. Anyway, okay, let's keep going. Okay, and then the reason to put it here is, the first half and will be the same for this term and this for all the diagonal terms. So h bar g n plus 1. Okay, and then h bar g n plus 1. Okay, and then n plus 1 half h bar g minus e minus h bar delta omega 2. Right, the determinant is this multiply this minus this multiply this. Right, so it's very, very clear. Okay, what this is. Right, this multiply this would be n plus 1 half h bar omega minus e square. Square, and then minus h bar square delta omega square 4, okay, and then minus h bar square g square, okay, n plus 1. Right, and the solution is fairly straightforward. Right, it's very clear what the solution is. Okay, you move this to this side, and then you do square root. So E will become, okay, n plus 1 half h bar omega, okay, and then plus minus, okay, plus minus h bar . There's a common factor h bar here, so you put it in the front. H bar delta omega squared divided by 4 plus g square n plus 1 square. Okay, plus minus. Okay, you see that the system, okay, the system now behave very interestingly, right? Behave very interesting. So before, right, you have your system has one energy, right? One energy is the energy. Well, let me put it in this way. Before, your system has two energy, right? Two energy. One. Okay, the system, the energy of a system. Let's just put it this way. Okay, a very simple analysis when we assume delta omega is 0, right? Let's assume delta omega is 0 for simplicity. Delta omega is 0 means that the energy between the ground state, excited state is exactly the same as the energy of a photon, right? So if there's no interaction, right? If there's no interaction, then the energy, there's only one eigenenergy in your system, or well, let me put it this way: the eigenstate, right, of the system is just degenerate, right? You can have the atom at the ground state, and then you have n plus 1, okay, n plus 1 photon, right? And this will be, and your energy will be this, okay? And then you can be at excited state and then have n photon, and you are at the same energy, right? At the same energy, right? And this actually makes sense, right? Because the energy is conserved in the cavity, right? So you only have one energy. when delta omega is 0. But here, okay, when looking at this solution, okay, what you will see is that if delta omega is 0, okay, delta omega is 0, because of the interaction between the photon and the atom, right, you will see that there's always energy splitting, okay, between the two eigenstate, even if your delta omega is 0, right? If your delta omega is 0, you now introduce g squared m plus 1 squared, right? So your energy is split in your system. If there's no interaction, it's like this, but now your energy is split. Energy, okay, this is delta omega equals 0, so this is h bar g m plus 1. H bar g m plus 1. Okay, and this will happen even if n is 0, right? Even at n equals 0. Okay, when n equals 0, you still have this splitting. Okay, and this splitting is caused by the vacuum, okay, interaction, again between the excited state and then your vacuum. So this is called I think it's called Robbie splitting. Let me see if I put it anywhere in the note. No. Okay. Anyway, yeah, this is called Robbie splitting. And then also called Robbie vacuum splitting, okay, if n equal to 0. And Robbie vacuum splitting, okay, is experimental evidence showing that your single photon and single atom, okay, your photon, your cavity inside this your atom inside this cavity is in the strong interaction regime with the atom, right? And then the Robbie splitting, and then commonly people write this down as n plus 1/2 h bar omega, okay, and then plus minus, okay, plus minus this, okay. So here there's a 2 here. Later we'll see why there's a 2. So omega r here is called Robbie frequency. And as you can imagine, okay, this was first discovered by Robbie, right? That's why the name is here. And omega r, okay, notice that there's a 2 here, is square root delta omega squared plus 4g squared m plus 1 squared. Okay, so this is the this is the Robbie splitting, Robbie frequency. And how do you see this in experiment? How do you actually see this in experiment? Okay, so one thing you will actually see is that you can try to measure the eigenstate of the system. Okay, you can try to measure the eigenstate of the system while you can, for example, you can tune the delta omega, right? You can tune for example, the frequency of the frequency of your cavity, right? By changing, for example, by changing the distance between these two mirrors, you can change this omega. In fact, you can change this delta omega. The capital omega cannot be changed, right? Well, typically people don't change capital delta omega because capital delta omega is your atomic frequency. So in experiment, what you can do is that you can change delta omega, and then you try to measure the eigenstate. Okay, try to measure the eigenenergy. Okay, eigenenergy of the system. Then, if there's no interaction, for example, if there's no interaction, if G is 0, right? G represents the interaction strength between the atom and the photon. Then what you will see is that you should see this. Okay, you should see this. So when delta omega is large, that means you have more energy in the photon. Then this one should be 1 n plus 1 state, right? And this would be 2 n state, right? 2 n state, okay? And okay, and now because there's interaction, okay, because there's interaction, and then if you look at the eigenenergy here, right, eigenenergy here, you will see that if G is not 0, right, G is not 0, then these two eigenenergy E plus and E minus, let's just put E plus, E minus, okay, E plus and E minus, they will never touch each other, right? They will never touch to each other because this term is never 0, right? This term can never be 0. So you would see, okay, your actual eigenenergy look like this. And then there is a splitting, okay, and this point, when they're closest, correspond to delta omega equal to 0, okay? And then the distance between these two, right, the distance between these two, as you can see here, is omega r, h bar omega r, right, or 2g n plus 1, right? So in experiment, what people do is that they measure this, and then they see, okay, whether there is a visible splitting, or this is called anti-crossing, okay, visible anti-crossing. And if there is, then people can conclude that, okay, this is in a strong interaction regime where your atom interact very strongly with the photons, okay, with the photons. Okay, now let's look at what this Robbie splitting, okay, will cause some. Well, what interesting phenomenon with this Robbie splitting gave us, right? So one of the very interesting thing, okay, is actually we can use this Robbie splitting to as a photon number selector. So what we can do is that we can input a photon, okay, from left into the resonator, into the cavity, right? And what you can see is that, okay, the photon, okay, can enter the cavity only when, okay, the photon energy plus the atom energy equals to the eigenenergy, okay, of the system. If it doesn't equal to that, you're not a stable state, right? Then you will be reflected. You're not going in, right? And if you're going in, then you can also be transmitted, right? So you can watch the transmission of the system, and then as a function of the photon energy omega, okay, photon energy omega. Photon energy omega p. Here omega is the frequency of the cavity. Omega p is the frequency of the input photon, right? Okay, omega p is the frequency of the input photon. Then if there's no photon, okay, if there's no photon inside, then what we can see is that, well, if we input one photon, right, there's originally no photon inside, we just input one photon. Then we know n equal to 0, okay, n equal to 0, and we work in the assumption that delta omega is 0, right? Then the splitting of the system, okay, splitting of the eigenenergy, right, okay, is 2 h bar g, right? Okay, this is one photon. Okay. one mistake here. I think there's no square here. Okay, there's no square here. Yeah, sorry I'm making too many mistakes. Okay, delta omega is 0, n is 0. Then you would have, okay, and the atom originally in the ground state, okay, in the ground state, then you have G coming out, H bar G, so 2 H bar G, okay, this is fine. And then when now, if you input 2 photon, okay, then the splitting n equal to 2 now, and the splitting become larger, right? The splitting become 2 H bar G, okay, 2 come from the plus minus, and square root of 2, right, square root of 2. So it becomes square root of 2 larger splitting. And then you can, keep going, right, if you have 3 photon. 3 photon, okay, then let's keep going up, right? So then what this cavity, okay, with an atom inside can do, okay, is that it can selectively pass the photons, okay, different number of photons. So for example, at this specific frequency, it only transmits the photon state with 1 photon. Okay, if your state has more than 1 photon, it will be reflected. So this is very interesting. Okay, so if you use it, then you can just keep sending random photon number onto here, onto the into the cavity lens. Then it will reflect all of those that is more than 1 photon or have no photon, and only pass those with 1 photon. It's very interesting. And then if you tune the frequency of the input light into a different wavelengths by different frequency, then you can start to transmit 2 photon state and then reflect 1 photon, 3 photon, or other photons. So this become a very nice photon number selector. Okay. Now the final part, okay, of this lecture would be we're going to solve the something called Robbie oscillation. Okay, it's the time evolution of the system. Suppose that we suppose we have n plus 1 photon, and then in the excited state, in the ground state, okay, and then n plus 1 photon. For example, if we start from this state, and then how it will evolve, right? So how a system will evolve with time, right? So basically what we do, okay, so we assume, okay, your quantum state is in a superposition, let's say AT plus, okay, BT. Right, and then evolve with time, and then you can give them initial condition, right? And apparently, okay, we need to use to solve the evolution. We need to use a time dependent Schrodinger equation, okay. Right, and then of course we need to use the Hamiltonian here, right? The Hamiltonian is important. Okay, and here we want to kind of simplify the simplify all the math here. So we assume delta omega is 0, right? Delta omega is 0. So this term and this term are the same, right? So if you look at this, the left-hand side will become n plus 1 half h bar omega, okay, and then h bar g n plus 1, h bar g n plus 1, and then here is the same, n plus 1 half h bar omega, okay, and then the matrix form of this is just A, T, B, T, right? AT BT. This is the left-hand side. So left-hand side, you will get okay, and then plus. Okay, so this is after this is just a vector, right? So here is the same as the okay, this equal to the right hand side I h bar. Okay. Okay. When you look at here, okay, something very obvious will show up is what to do with the first term, right? So the first term is just a simple time evolution. So if you let A t become AT e to the minus I, and this is its energy. Let me just okay, minus h bar omega. There's no h bar. Okay, so minus I m plus 1/2 omega t. Right? If you kind of plug this back in, you will see that the time derivative will make this come out, right? M plus 1/2 h bar and then minus I times with this I become 1 and h bar, okay, is h bar here. So this is just a simple the phase oscillation, right, of your the eigenstate. So here by making this, you can call this rotation frame, okay, both on A and B. What you can do is you can get rid of this term. I can get rid of this term. Or if you want to be like mathematically more accurate, then what you can do, I think, is you can call this A prime, right? If you plug in this back in, then you can see that you can cancel out all this term here. Okay, so so what we end up with, is two equations. Okay, one is, and they're coupled together, right? The first equation is the time derivative of A give you B, and the second equation is the time derivative of B give you A, right? And we're kind of very familiar with this type of equation. This type of equation either give you exponential increase or decrease, or it give you sine and cosine, the oscillation. So here it's a second case. Right, let's write them down in a better form so that we know what to do with them. AT, okay, you can cancel the H on both sides, and then I become minus I, come out this side. So I, G, BT. Okay, I think this is the right one. And then you have BT. It's exactly the same. Right, and the way to solve this is very simple. You do a time derivative of A, of the first equation, and then you get the time derivative of B here, and then you plug it in. Right, so yeah, partial square, partial t square, AT equal to minus ig square root n plus 1 partial t bt, right? And we know partial bt is just this, so okay, you just get square at. All right, just get this, and then yep, okay, and then this is g square I, you have minus sign here, n plus 1 at. Right, so you end up with this equation equal to, well, plus okay. So I don't know if you guys you know, kind of recognize what type of solution this is, right? So the second derivative of a function plus a constant times that function equal to 0. So the solution is, of course, sine and cosine, right? Sine g n plus 1 okay, t, and then also cosine n plus 1 t, right? Because sine, we're to do twice derivative, okay, this will come out twice and there's a minus sign, right? So these cancel each other. So you can see that the solution of A, okay, solution of A C1 plus C2, right? The solution of A is just a combination of two oscillation terms, right? If we start with if we start with A at t equals 0 as 1, right? If we start with ground state, then what will happen is that, okay, sine is, the C1 goes to 0 now. And what you have is a cosine oscillation, right? Cosine oscillation of AT. And then let's see if initial condition, right? Initial condition, the C1, C2 has to be solved by initial condition. If initial condition is A, t equals 0, okay, is 1, right, then C1 is 0, C2 is 1, okay, C2 is 1. Then you will see that the probability of the, where is the electron, right? You calculate the probability, okay, and A is the probability at the ground state, B is the probability at the excited state. So A t square, okay, will equal to cosine square, okay, G, right? So this is a cosine square oscillation. And then if you calculate BT, right, BT of course is 1 minus AT square, right, because your probability is always 1, right, so it's sine square G, okay. So now we know, okay, what really happened. Let me erase this. Okay, in the system evolving with time, right? Suppose, yeah, this is A square. Right? Yep, this is T. Right, suppose you first start with the ground state and then with n plus 1 photon, right? And then after a certain time, okay, you will be at, this is 1 n plus 1, okay? You will arrive at excited state where you only have n photon, right? So it's like 1 photon is being absorbed by the atom, and then you will come back again, right? You'll come back again and come to here, and then keep going and keep going, right? So this, so your system will behave as an oscillation. The atom, okay, will come up, go down, come up, go down, come up, go down, and then your photon number will increase by 1, decrease by 1, increase by 1, decrease by 1. Okay, and this oscillation, okay, the period of this oscillation, pay attention here, is not g square root n plus 1, right? Because you have a square here, right? You have a square here, so the actual oscillation period is 2g n plus 1. Okay, 2g n plus 1. I don't know if you guys notice what this is. If you guys recognize what this is. We previously give you guys a definition of Robbie oscillation, right? Robbie oscillation. Right, Robbie oscillation, Robbie frequency, and in the case where the delta omega is 0, okay, this goes to 2g n plus 1. Okay, so you see that the oscillation is the Robbie frequency. Okay, this is actually the physics meaning of the Robbie frequency, and that actually explained to us, okay, why when we define Robbie frequency we have to define like something like this. There's a factor of 2 here. Okay, the factor of 2 here is just to match the physical oscillation period. Okay, so Robbie oscillation is something extremely important in quantum information and quantum computing, and but we're just giving you this very simple model, and we're not going into any details here. Okay, so here I think in these 2 lectures I give you guys kind of some idea of the full quantum model, and I apologize that the next 2 lecture, okay, the final 2 lecture, we'll talk about something very specific in quantum optics, is the squeezing, and two-mode squeezing specifically, that create entanglement. And after that, okay, we will conclude this semester. Okay, thank you guys.